Welcome back to the channel. Today we will start with Part 8 of Applied Physics 1, and we'll cover about special theory of relativity. Let's get started. We will cover the following contents in this video. So, let's start with our first topic. The special theory of relativity, developed by Albert Einstein in 1905, revolutionized our understanding of space, time, and motion. This theory addresses the physics of objects moving at high speeds, particularly those approaching the speed of light. The special theory of relativity applies to inertial frames of reference, where no acceleration is involved, and shows how space and time are interwoven. A frame of reference is a coordinate system used to describe the position, orientation, and motion of objects. It provides a perspective from which observations are made. In the context of relativity, the concept of different reference frames becomes crucial. Types of reference frames are: inertial frame of reference. An inertial frame is one in which an object either remains at rest or moves at a constant velocity, provided no external forces act upon it. In this frame, the laws of physics are the same and hold uniformly, that is, no net acceleration occurs. Non-inertial frame of reference. A non-inertial frame is one that is accelerating or rotating. In these frames, fictitious forces like centrifugal force or Coriolis force must be introduced to explain the motion of objects. Relativity of motion. Motion is always relative. For example, a person sitting in a moving car might perceive themselves as stationary relative to the car, but a person standing by the road will observe the car and the person inside moving. Importance in relativity. The theory of relativity deals with how different observers, in different reference frames, which may be moving relative to each other, perceive time, space, and the speed of objects. The Michelson-Morley experiment, 1887, was one of the most famous experiments in physics, designed to detect the presence of a hypothetical medium called the luminiferous ether through which light was thought to propagate, much like sound waves propagate through air. The results of this experiment had profound implications and paved the way for Einstein's theory of relativity. Aim of the experiment. The ether was thought to be a stationary medium filling all of space, through which light waves moved. The goal of the experiment was to detect the Earth's motion relative to this ether by observing changes in the speed of light when measured in different directions, with or against the Earth's motion through space. Experimental setup. The setup involved splitting a beam of light into two perpendicular paths, reflecting them off mirrors, and then recombining them. The interference pattern would show changes if the speed of light varied depending on the direction of the Earth's motion through the supposed ether. Expected outcome. If ether existed, there would be a difference in the speed of light between the two paths, leading to a detectable shift in the interference pattern due to the Earth's motion through the ether. Result. To their surprise, no significant change in the interference pattern was observed, regardless of the orientation of the apparatus. This null result suggested that the speed of light was the same in all directions, regardless of the Earth's motion. Impact. The failure to detect the ether led to the conclusion that it did not exist, challenging the then accepted view of light propagation. This result was a key factor leading to the development of Einstein's special theory of relativity, which showed that the speed of light is constant in all reference frames and doesn't require a medium to travel through. Einstein formulated the special theory of relativity based on two simple but revolutionary postulates. First postulate: principle of relativity. The laws of physics are the same in all inertial frames of reference. This means that no particular inertial frame is special or preferred. Observers moving at constant velocities relative to each other will observe the same physical laws. Example, laws of motion, electromagnetism. For example, Whether you're on a moving train or standing still on a platform, the fundamental laws of physics remain unchanged. Second postulate: constancy of the speed of light. The speed of light in a vacuum, denoted as c equals 3 multiplied by 10 to the power 8 meter per second, is the same for all observers, regardless of their motion relative to the light source. This means that even if you're moving toward or away from a source of light, you will measure the speed of light as the same constant value. This was a dramatic departure from classical physics, where the speed of objects would be expected to vary depending on the motion of the observer. Consequences of special relativity. These two postulates lead to several counterintuitive and groundbreaking conclusions about the nature of space and time. Time dilation. Time is not absolute and can flow at different rates for observers in different inertial frames. According to special relativity, a clock moving relative to an observer will tick slower than a clock at rest with respect to the observer. This is known as time dilation. Example: an astronaut moving close to the speed of light will age more slowly than people on Earth, as seen from Earth. Length contraction. Objects moving relative to an observer will appear contracted, shortened, along the direction of motion. This phenomenon is called length contraction. Example: a spaceship moving near the speed of light will appear shorter to an external observer on Earth. Relativity of simultaneity. Events that appear simultaneous to one observer may not appear simultaneous to another observer in motion relative to the first. This challenges the classical notion of absolute time, suggesting that the concept of now depends on the observer's motion. Mass-energy equivalence. One of the most famous outcomes of special relativity is the equation E equals mc squared, which shows that mass and energy are interchangeable. A small amount of mass can be converted into a tremendous amount of energy, as demonstrated in nuclear reactions. Lorentz transformations are a set of equations that relate the space and time coordinates of events as measured in different inertial frames of reference moving at a constant velocity relative to each other. They are essential for understanding how quantities like time, space, and velocity change between different reference frames in the context of Einstein's special theory of relativity. The transformations are based on two key assumptions. The speed of light is constant in all inertial frames of reference. The laws of physics are the same in all inertial frames of reference. Lorentz transformations replace the classical Galilean transformations, which assume absolute time and space, with a new way to link the coordinates and times of events in different inertial frames. Let's consider two reference frames. Frame S. Stationary, an observer at rest in this frame. Frame S' moving, an observer moving at a constant velocity. V relative to frame S along the x-axis. Let an event occur at time t and position x, y, z in frame S. The same event is measured in frame S' at t' and position x', y', z'. The Lorentz transformations relate these coordinates as follows. Lorentz transformations for space and time, where gamma is the Lorentz factor, which becomes significant at velocities approaching the speed of light. V is the relative velocity between the two frames. C is the speed of light. Explanation. Space contraction. The term x minus vd shows that distances along the direction of motion contract for an observer in the moving frame. This is the basis of length contraction. Time dilation. The term t minus vx divided by c squared accounts for the fact that time runs differently for observers moving at different velocities, leading to time dilation. Key points. At low velocities, v much less than c, gamma is almost equal to 1, and the Lorentz transformations reduce to the classical Galilean transformations. As v approaches c, the effects of time dilation and length contraction become significant. Lorentz transformations for velocity. The Lorentz transformations also affect how velocities transform between two reference frames. If an object moves with velocity ux along the x-axis in the stationary frame S, the corresponding velocity u-x in the moving frame S- is given by velocity transformation, where u-x is the velocity of the object in frame S-. Ux is the velocity of the object in frame S. V is the relative velocity between the two frames. C is the speed of light. Key points. Relativistic velocity addition. In the realm of relativistic speeds, velocities do not simply add up as they do in classical mechanics. As u-x approaches c, the velocity in frame S- also approaches c. This ensures that nothing exceeds the speed of light. For velocities much less than c, which we call non-relativistic speeds, the transformation reduces to the classical u-x equals ux minus v. This is the simple Galilean velocity addition. Applications. This formula serves a crucial purpose. It ensures that even when adding high velocities, the resulting speed never exceeds the speed of light. This is a fundamental requirement in relativity. Mass-energy relation. One of the most famous results of Einstein's special theory of relativity is the mass-energy equivalence relation, E equals mc squared, where E is the energy of the object, m is the mass of the object, c is the speed of light in a vacuum. This equation shows that mass and energy are interchangeable. A small amount of mass can be converted into a large amount of energy because is a very large number. This principle is the basis for nuclear reactions, where small amounts of mass are converted into enormous amounts of energy. Implications. The equation explains why nuclear reactions release so much energy. In both nuclear fission and fusion, a tiny amount of mass is converted into a massive amount of energy. It also implies that mass itself is a form of energy, and objects with mass can be thought of as having a huge amount of potential energy, even when stationary. Rest mass energy. The energy associated with the rest mass m0 of an object is called rest energy, given by E0 equals m0 c squared. This represents the energy an object has simply by virtue of having mass, even when it is at rest. Total energy. When an object is in motion, its total energy E. E includes both its rest energy and its kinetic energy. E equals gamma m0 c squared. Quick summary. The special theory of relativity fundamentally changed how we understand space and time. It showed that space and time are not fixed, independent entities but are interconnected and relative, depending on the observer's state of motion. The Michelson-Morley experiment and the postulates of special relativity laid the groundwork for modern physics, providing insights into phenomena that occur at high velocities, especially those approaching the speed of light. Lorentz transformations provide the mathematical framework to relate space and time coordinates and velocities between observers in different inertial frames of reference. They highlight how time dilates and lengths contract when objects move at relativistic speeds. The mass-energy equivalence relation shows that mass is a concentrated form of energy, with enormous implications in fields such as nuclear physics, astrophysics, and particle physics. That's it for today's video. We have completed all the topics for Applied Physics 1. From the next video, we will look into some numerical problems based on the topics we covered. Till then, please like, share, and subscribe to the channel. See you in the next video.